So, welcome everyone. It's great to see such a fantastic turnout. And a big thank you for those of you who are watching us via the live stream. So in light of opening the new region here today, I thought it would be a perfect opportunity to kind of cover some of the design principles for architecting best practices. So the 5 things that I'm going to cover today are elasticity, designing for failure, designing loosely coupled systems, we'll touch on security, and then I'll finish off with looking at performance. And as any technical presentation wouldn't really be complete without a live demonstration, fingers crossed, assuming that the sort of the ticky gods will allow us, I'm going to do a few live demonstrations today as well. So let's get started. So in terms of elasticity, I'm going to talk about a few services which help customers produce highly elastic systems. The first one that comes to mind is obviously EC2, our Elastic Compute Service. This allows customers to install any manner of operating systems, Windows, Linux, the enterprise versions, but also the community-supported versions too, on top of a virtual compute resource and run that in our AWS cloud. The second component of relay architecting for elasticity is the Amazon CloudWatch service. So the Amazon CloudWatch service allows us to monitor key metrics inside of our resources, such as, for example, if we were looking at EC2, it could be what's the I/O to disk, what's the CPU. And even better than that, we can actually look across groups of servers. So we can look at things like statistical averages, maximum and minimum values across a group of servers. The third service, which is often used to design highly elastic architectures or systems, is the auto-scaling service. And this allows us to scale up and to scale down or out and in EC2 resources, depending upon environmental conditions, such as, for example, increased load on your website or something similar. So by combining our CloudWatch service, EC2, and auto-scaling, we can actually create a highly scalable architecture. Now, as our web server tier, let's say, scales out, we need some way to decouple the consumer, the client behind their browser, and that web server tier. Now, that's commonly done in a traditional sense by using a load balancing service. Now, AWS provides an elastic load balancing service. And this allows us to distribute traffic across all availability zones within a given region. So by placing the elastic load balancing service in front of our web tier, as the web tier scales out and scales back in, we have that kind of constant endpoint for our customers to connect to. So let's take a look at what might happen through maybe a typical day for an e-commerce customer. So maybe at 6 a.m. in the morning, the load on the system can be sufficiently catered for with a single web server. As the day progresses, and now we get to, say, 10 a.m. in the morning, we find that the average CPU across that one single server maybe is now 80%. Now, using auto-scaling, we can define a rule which states when the average CPU gets to, say, 80%, add another resource to our auto-scaling group. So the auto-scaling rule has triggered. We've created a new web server, and we've now placed it behind the load balancer. Obviously, the first thing we need to do is some sort of a health check to ensure that before we deliver our production traffic to that web server, that it will be able to handle that. So the load balancing service actually has that feature. We can do health checks. Once the health checks have been passed, the load balancer then distributes traffic to both of those web servers. And consequently, because we're distributing traffic across them both, the average CPU now has come down. So if it was 80%, logically now it's about 40%. Now this is great for scaling up, but if all you ever did with your architectures was scaled up, then you're missing some real economies, some real sort of cost-saving opportunities. So let's fast forward now to 7 p.m. in the evening, and we find that the average utilization has now decreased significantly. Maybe it's now, say, 50% across the 2 web servers. So we could have a rule which states when the average CPU gets to 50%, remove one of those resources. The instance is terminated, and then the load balancer continues to serve customers by distributing all of the traffic now to the last remaining web server. Okay, so part 1 of the demonstration. So today I'm going to demonstrate auto-scaling by using the services that I've just introduced, so the load balancing service, auto-scaling, CLOUDWATCH, and EC2. And I'm going to apply some load to my auto-scaling groups by using something called bees. But these are no ordinary bees. These bees have machine guns. They're killer bees. Okay, so what we're going to do now is just have a look at some historical data, just in case the demonstration doesn't work, and you'll see what I hope to replicate in the next few minutes. So this page here is showing my 2 web servers that I currently have in my auto-scaling group. Here you can see a history of some previous testing that I did yesterday to demonstrate how the auto-scaling rules actually keep the average CPU across my web server tier, between sort of 75 and 100%. So this is the average CPU we're looking at. And the next slide here shows the cumulative CPU across all of those web servers throughout that time. And as we can see, it varies from less than 300 right to over 500 at its peak. Okay, so let's see if we can replicate this today in half an hour. So I'm now logged on to an EC2 instance in the AWS cloud. And what I'm going to do is I'm going to, first of all, check that my bees are ready to attack my AWS ELB endpoint, and they are. So I'm now just about to instruct them to all attack this load balancer, and actually no. So I'm now going to instruct them all to attack a given load balancer, and once that's complete, they will then go back to rest and await further instructions. Okay, so the bees are being assembled, and they're getting ready to fire their machine guns. So let's come back to this maybe in sort of 20, 25 minutes later, and fingers crossed, we'll have some results to share. Okay. Oops. So the next thing we need to look at is designing for failure. As Werner Vogels, our CTO of Amazon.com, has actually said, everything fails all of the time. So the way to avoid failure is to design for it. So your goal when you're running an application on AWS should be that the application should continue to function even if the underlying physical hardware fails, or it's removed, or it's replaced. So in a similar way to what we do in a physical environment or a virtual environment where we look through for single points of failure, there may be network switches, web servers, application servers, database servers, etc. We need to look for these single points of failure in our architecture. And then by assuming that everything fails, we can design backwards. So if we assume that half of our architecture will actually fail at any one given point, we need to be able to ensure that service is still provided to our customers. One of our services that really helps customers design highly available architectures is our relational database service, RDS. Now, while customers are quite entitled to run whatever database service they wish on top of EC2, for those customers that want to consume a managed database service, we have RDS. So as a few of the speakers have talked about today, it comes in 3 variations. It's a managed Oracle database, SQL Server, and MySQL. So let's take a very simple web database architecture. We have our web server. We have our database server. If we wish to make this public, usually we would attach a fixed public IP, so an elastic IP address. And then we can create a DNS record which maps www.mydomain.com to that web server. While you're entitled to use whatever DNS service you wish, you can actually use Route 53, which is our domain name service. So you can define your CNAMEs and A records, etc., and allow our highly durable, highly scalable infrastructure to provide those DNS services. So this is how it changes our architecture. Now, I'm sure you're thinking, well, Daniel's already introduced the concept of a load balancer, so I think we can probably do a little bit better than this. So let's take a look at the web server tier. In the event where the web server fails, what we need to do is fail across this elastic IP address, and then obviously there'll be a small momentary disruption to service, and then we can continue providing service to our customers. I like to tackle this problem with a slightly better solution, which is to use the elastic load balancer. Because if at all possible, you don't want to have any outages of your particular web service. And well, so this will protect us in the case where one of those web servers is terminated for some reason, but what happens if both of them do? Or what happens if our website comes under increasing load? Well, we really should think about using auto-scaling effectively here, not just to protect from increased load, but also to provide a self-healing architecture. So now we have a relatively simple web app that uses auto-scaling. It's got redundancy at the load balancer tier, but there are still a few single points of failure. The relational database service, RDS, allows us to deploy a multi-AZ solution. And what this means is that we can have a master database server in one availability zone and have synchronous replication over to a slave database server in a secondary availability zone. So in the event where, for example, the master database server is unavailable, or you needed to change the size of that database service, we can fail across to the slave, which is a synchronous copy, and service is maintained. In the event that we've had a failure, we then simply create a new slave, which is then once again a synchronous copy of the new master server. The availability zone B is looking a little bit bare, though. So let's look to stretch our other resources across both availability zones. So one of the benefits of auto-scaling groups is that we can actually stretch these resources across multiple availability zones within a given region. And because the elastic load balancing service is inherently fault tolerant, we're now able to have an architecture that can operate both simultaneously and independently of failure of a given availability zone. Okay. So let's now take a closer look at the Amazon CloudWatch alarms. So far we've been using CloudWatch to generate trigger points to do scale up and scale down events. And these are really good if we want to automate processes, scaling up, scaling down, etc. As you can see here, we're actually looking at what the CPU utilization is across a given EC2 instance. We can provide histories of this data, and we can also create what's called custom metrics as well. So for example, imagine if you wanted to track and to monitor what the memory utilization is of an EC2 instance. by using a custom CloudWatch metric, we can actually do that. There's a large degree or a large selection of metrics that we can choose when we're creating our alarms. So in this simple example here, we're actually going to look at network I/O, and we're going to create an alarm when the I/O goes above 8 megabytes per second throughput. And alarms can be sent to either like an email recipient using our simple notification service. They can also be sent to HTTP endpoints, and they can also be sent to our SQS service, our simple queuing service. In this simple example, we're going to send an example of our CloudWatch alarm to an email address. An alarm will have some sort of a metric which will cause the alarm to trigger. And it may be, in the case of this, if the network I/O is above 8 megabytes per second for a period of, say, 5 or 10 minutes, then trigger the alarm. And here you can see what a typical alarm would look like if it was sent to an email recipient. Now, it's very powerful being able to receive an email when there's a change in state within your environment. But what's even more powerful if you start to integrate these alarm services and these notification services with automated web services. So imagine you have a monitoring service within your enterprise environment. And when one of these alarms trigger, it actually receives a notification message instead of a human. Okay. So as was mentioned earlier, we have over 30 different sort of services that we provide. And they're, mostly they are inherently fault tolerant as services. However, you should be aware when architecting systems that services like a single instance of EC2, like that's a specific resource of EC2, we need to design for failure from that specific instance. Because while the service itself is tolerant to failure, that particular instance is sitting on physical hardware somewhere inside of the AWS infrastructure. And as Werner said, everything fails all of the time. So it's important to know which services are inherently fault tolerant and which ones we actually need to pay some attention to when we're architecting our systems. Customers like the likes of Netflix have obviously created very highly scalable, highly durable architectures on top of AWS using these sort of basic building blocks. And one of the cool things that's come out of the Netflix team to help them design and test for failure is the Chaos Monkey. So the Chaos Monkey is a way for us to introduce failure into our architecture. So the way the Chaos Monkey works is you tell the Chaos Monkey how frequent to run, every minute, every hour. And then you tell it what's the probability that you will terminate a single instance within an auto-scaling group. Okay? And hopefully, if you've configured the Chaos Monkey correctly, it won't cause complete sort of havoc within your infrastructure. So I'd highly encourage anybody here today who is really interested in sort of sysops to actually take a closer look at the Chaos Monkey. They open sourced this, so it's now available on GitHub. And I'd highly encourage you to check out the official blog of the Netflix team. Okay, demonstration part 2. So first of all, let's take a look at what's been happening with our bees with machine guns. And maybe let's introduce the Chaos Monkey to the demonstration. Okay, so let's go back to my summary page. Good. So we can currently see that there are now 3 web servers running in my auto-scaling group. And if we look at if I'll just zoom in here, if I look at the last hour's worth of data, you can see this here is the average CPU. There's quite a significant spike has occurred in the last sort of 15 minutes. since I instructed the bees to attack my elastic load balancing service. And the average there is pretty close to 100%, I think you'd agree. If I now look at the cumulative CPU, you'll see that the cumulative CPU has gone way above 100%, and it's actually peaked there over way over 200%. So far, so good. So let's make the autoscaling service work even harder, and let's introduce the Chaos Monkey. Okay, so just excuse me for a moment. So the way the Chaos Monkey is going to work is every minute the Chaos Monkey will start, and it will look to destroy one of those resources, which I hope will increase in the coming minutes, with a probability of 10%. So for the remaining part of today's session, we probably should see maybe 2, possibly even 3 instances being terminated by the Chaos Monkey. And to ensure that we see what happens, I'm going to just tail a log file that's being created by the Chaos Monkey. Okay, let's get back to the presentation. Okay, so part 3, the third design principle for architecting for the AWS cloud. It's around loose coupling. So the idea is for us to build loosely coupled systems, because the more loosely coupled systems are, the bigger they can scale. So if at all possible, we wish to create independent components. I'll give you an example of a tightly sort of coupled system. Imagine as your web server scales up, your application server needs to scale up as well. So you'll have a one-to-one mapping between web and application server. That's not really going to scale very well. It's very tightly coupled. When you are designing systems, try and think of them as publishing them as services, and also consuming services as black boxes. So I don't need to know the inner workings of how the elastic load balancing service works. I just need to know what the feature set is and basically what the API set is. Let's take a look at a common decoupling challenge. So imagine we have a website that allows users to upload multimedia. The multimedia then gets encoded, and then the encoded version is then stored in the cloud. If we have a receiver pushing jobs to an encoder and publisher, this is another example of a very tightly coupled system. So let's make things a bit more interesting and a bit more flexible. Let's introduce a queue to this architecture. So now when the receiver receives a job to encode, for example, a video, we place a job on the queue. And then the transcoder and publisher pulls those jobs off the queue as quickly as it can. The key thing to note here is the rate at which jobs are placed on the queue is actually different, or it can be different, to the rate which they're taken off that queue. So imagine that we develop our receiver service in Java. We could deploy the Java app in the Elastic Beanstalk service. And when the user uploads some content, it interacts with the application running on Beanstalk, and then Beanstalk pushes the content out to S3. So how are we going to implement the queuing component of this architecture? Well, we can use the Amazon Simple Queuing Service, SQS. So once the content has been uploaded to S3, we define a new job, and we place it into the queue. And then, using a combination of EC2, autoscaling, and CloudWatch, and maybe CloudWatch will be monitoring the size or the number of items on the queue, we can then scale out and scale in our transcoder and publishing instances. Now that's all very good for a very simple process flow that involves receiving and transcoding and publishing. But real life is a bit more complicated than that. So for a real life example, we need to do different things like check the video size. Is it too long? If it is, we need to shorten it. Check the content. Is it appropriate? Is it spam? And after those sort of checks have been passed, then we undertake the process of transcoding and publishing the content. So let's see how this relatively simple architecture would change if we needed to have all those different steps. So, while this is still a viable architecture on AWS, we now have 4 different queues, and each queue basically contains a series of tasks that need to be completed. It's starting to look a little bit complicated, though. It's going to be pretty hard to maintain. If we ever need to make a change to the process, that's a business process, we're going to need to deploy additional resources. It's going to be a little bit tricky to audit and actually see how a specific job flows through the entire queue. And for those of you that have worked with SQS, it's a great service, but it's probably a little bit too low level for this particular use case. So what are we actually trying to do here? So if we look at the process flow, what we see is that it consists of a series of tasks and also a series of decisions. And it would be great also if we could have a history of jobs as they sort of flow through our process. And if we can make the whole thing stateless, that's even better. Because we all know that stateless scales horizontally. How we can solve this is using the Amazon Simple Workflow Service, SWF. So SWF works by keeping a track of state. It allows us to have executed tasks, keeps track of things like timeouts and errors, so it's very easy to audit. And how it does this is it has basically 3 components. We have our decider component, which basically makes decisions based on the history of a given job in a workflow. We also have these worker components, which actually carry out the work. And then we have the Simple Workflow Service part that basically stores the state for each one of these jobs in the queue. So the deciders, the way that they work is they poll for work on a decision from a decision list. They evaluate the workflow execution history, and then they return a decision to the Amazon Simple Workflow Service. And when they're finished, they go back to the beginning and then just do the whole thing all over again. The worker components, they work by polling for a job from a specific task list. They execute the particular task in mind, and it could be encoding a video, it could be pushing that content to S3, it could be doing some sort of shortening of a video. And then they return either a success or a failure, and that goes back to the actual state history for a given job flow. Okay, so let's see how this can simplify our architecture. So now all we need to do is install our worker and decider components on, in this case here, EC2 instances. And we've now, that now allows us to replace a significant proportion of the complexity that we saw in the previous architecture. And we'll take a closer look at this in a moment. One of the great things about the Simple Workflow Service is that all of the scalability best practices that I've talked about and you can find on our website, they all apply equally well here. So there's nothing stopping us placing our worker nodes. These are the things which obviously execute tasks inside of auto-scaling groups. Similarly, for when we have the case of large numbers of jobs, it may also make sense to have our decision-making components also inside of autoscaling groups. And hey, while we're at it, we might as well distribute our load across multiple availability zones within a given region. This allows for, obviously, fault tolerance in the event where we have a partial disruption to service in a single AZ. The simple workflow service isn't just restricted to the AWS environment. So if you wish, you can install and you can use a simple workflow service inside of your existing enterprise architecture or infrastructure today. And you can either run it wholly from inside of there, basically consuming the web service, or if you wish, you can have a hybrid solution. So in the case of needing to burst into the cloud, maybe we can have one or more of our worker nodes running on EC2 inside of the AWS cloud. So by using the simple workflow service, we can take a relatively complex, difficult to manage architecture like this and replace it with something that resembles this. One of the great things about the simple workflow service is we don't require you to learn a new programming language. So if you're a Java or a .NET developer, PHP, Perl, whatever it is, you can still continue to use those languages with the simple workflow service. However, if you are a Java developer, there are some benefits. So we developed this thing called the AWS Flow Framework, and that allows you to develop your entire workflow and express it in sequential code. So if this is of interest to you, I'd highly recommend you check out the SWF section of our website. Okay, so how do we decide whether to choose SQS or to use simple workflow? There's no real right and wrong answer here. I'm going to give you some guidance, though. If your process flow requires some element of making a decision, then it's good practice to use a simple workflow service. However, if there is no decision logic in your architecture, then a simple queue will probably suffice. Okay, section 4, security. Now, AWS treats security as our #1 priority, and I simply cannot cover off security in as much detail as I'd like to within the remaining sort of 10 or 15 minutes that I have. So I'm going to cover off a few of the key areas and then recommend that you go to the security section of our website certainly for further details. Either that or come and have a chat with myself or some of the other members of the SA team over in the booth at the end of the session. So as Andy Jassy mentioned earlier, we have a service called Identity and Access Management, IAM. And that allows us to basically restrict access to resources to users and groups and roles within your organization. So when you create an AWS account, you'll have a username and a password. And that will obviously have full control over the resources that you own. With IAM, what we can do in this case here is create 3 separate groups. There's one group for admins, and they may have full access to resources. There's another group for developers, and maybe we'll only allow the developers to stop and start EC2 instances, but never to terminate them or to create new ones. And then maybe there's a test group, and maybe we'll only allow those guys to actually start new instances. IAM provides multi-factor authentication. So you can use one of these Gemalto keys, like I have here today. Or you can use any software application that supports the auth TOTP protocol. And that's readily available for Android and iPhone, etc. Security groups. So security groups, think of these as like firewalls at the hypervisor layer, the layer that controls access to resources inside of AWS. And if we consider a traditional or a typical sort of 3-tier architecture, what we would typically do is create security groups for each one of those tiers. So we would have a security group for the web tier, one for the application tier, and also one for the database tier. And then we would restrict access to each one. So for example, we may only allow our Elastic Load Balancer to talk directly to our web server tier on port 80 and port 443, and never allow it to talk directly to the application tier or to the database tier. Similarly, we may have a security group rule which only allows the web server tier to talk to, say, port 8080 on our application server tier and never have direct contact to our database tier. Certification and accreditation. In the past, we've published multiple reports for SAS 70 Type 2. We're now publishing reports for SOC 1 compliance, basically the service organization's controls, in accordance with the SSAE 16 and the SAE 3402. We are ISO 27001 certified, and we have a PCI DSS level 1 compliance. So that's the credit card industry compliance. Now, it is a shared responsibility when you use AWS services, and it's very important to remember that when you're architecting your systems. We give you the tools to architect highly available, highly secure systems, but it really is up to you to actually use those tools effectively. And we have canonical architectures and best practice white papers to help you do that. And finally, we have some other certifications that are probably more relevant to the US market, such as FISMA and the DIACAP certification. Okay, and to finish off, we're going to take a look at performance. I've talked about scaling out and scaling in. We can also scale up in AWS. So as of today, we have over a dozen different EC2 instance types, ranging from virtual machines with small amounts of compute and say, almost 700 megabytes of memory, right through to very, very large instances, such as these cluster compute instances you can see here. So these have 2 Intel Xeon Sandy Bridge architectures, 8 cores, 60 gigabytes of memory, and over 3 terabytes of local storage. For those applications that would benefit from a general purpose graphical processing unit, we also have the cluster GPU instance types. These, once again, are dual Xeon quad-core Nehalem processors, and each one of them has an NVIDIA Tesla Fermi graphics card. Another area where people can benefit from performance is to cache and to buffer between the application tier and the database tier. Obviously, relational databases don't scale really, really well, unlike things like, for example, the DynamoDB service. So we want to try and obviously cache as many of the reads as possible. So what we can do is introduce an in-memory caching service, and we have a memcache compliant service called Elastic Cache. So what we're able to do is, instead of interrogating the relational database every time we need to do an SQL query, we can store common queries inside of the Elastic Cache service, and we hit that in-memory database first without having to go to the relational database. And finally, search engines. So I know an organization that's quite experienced at developing highly available, highly scalable search engines. So you can see here, really, any sort of properties of a search engine, it needs to have the ability to do things like relevance and ranking. We need to be able to do a faceted search, so select a subset of the total objects that we can search from. Maybe in this case here, only search from products from the gardening section. Being also able to search based on range. So for example, what's the average user rating, or maybe the cost of the item. And to do so, we've provided an Amazon Cloud Search service. So this came out of A9, which is a wholly owned subsidiary of Amazon. and basically allows us to do democratized search. So basically, for the cost of almost $100 per month, we're able to provide a fully managed search service in the cloud that can be set up and running in less than an hour, and it will scale automatically to your needs as the amount of data that it needs to index grows, but also the traffic to your service grows as well. The way CloudSearch works is we have two endpoints. One is a document upload endpoint, which is where we send our content to. And then we also have a search endpoint. This is where we basically make API calls to do the searches. And as we can see here, as the amount of data grows and also the amount of traffic grows, AWS automatically scales out our cloud search service. OK, so let's go back to our, say, our e-commerce site. And throughout the course of the day, our auto-scaling group for our web server tier grows and shrinks. But that doesn't really help us if there's a search component of this particular architecture. So what we can do is, by sending our content to our cloud search service, we're able to index that content and then provide that search functionality to customers consuming our web server. Now, one of a large number of canonical or blueprint architectures that we have and we publish in the architecture section of our website is media sharing. Let's see now how we can take the media sharing architecture and evolve it to add a search component. So with any media type of sharing solution, we'd probably be uploading PDFs, multimedia, images, MP3s, etc. So we convert these to the search document format, post the content to the upload endpoint, and then we can introduce CloudSearch into this architecture and allow our customers now to search based on the content of the shared media platform. OK, just to round things out, let's take a look at the demonstration and see what havoc the Chaos Monkey has caused. So we can see here that the Chaos Monkey has actually terminated 2 of my instances. So the Chaos Monkey has been doing its job. Let's take a look at the number of EC2 instances that we have. OK, great. We can see the 2 terminations, but we can also now see 4 running instances. So the auto-scaling rules have now been kicking in. They've been replacing those terminated instances, not just by the Chaos Monkey, but also from the additional load provided by CloudBees. So thank you to the demonstration gods. They allowed me to do the demonstration today. So just rounding this out, what I would say is AWS, really you should think of our services like a collection of Lego building blocks. You pick and choose whatever makes the most sense for the architecture that you're building. And all the best architectures evolve over time. So make some pragmatic decisions today and then return to your architecture over time. And over time, it will evolve and improve and become more highly available as your business scales to meet the demands of your customers. Thank you for listening.